The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
All right, our next presentation is on some renovation of historic structures. There's an awful lot of new stadium structures being built all the time, not only throughout this country but in other places. But certainly there are a number of these very noteworthy stadiums that it's worthwhile keeping around. And we're going to see a presentation on this next one by Matthew Sherman. Matt is a principal with Simpson, Gumpertz, and Heger in their Boston, Massachusetts office. Matt's been practicing repair and rehabilitation in concrete structures for over 20 years, and he specializes in really focusing on evaluation and rehabilitation of structures. So with that, we'll turn the program over to Matt.
Thanks, Ben. So I'm going to talk not necessarily about a particular project. It's really the approach that we take looking at a structure such as historic stadia are great examples going right along with what Dave was talking about earlier, really maintaining what we have, respecting the past, making it workable and usable for today's actions. So I'm going to go through a little bit at the end about how we did some of these stadia repairs in general, but really it's going to be about how we chose the scope of work and how we picked the approach that we were going to take to the work that we did. So I really like working at stadia are neat structures. They're open structures. They are what they are. They show you what they are. They're an open structure. What you see is what you get. They're very utilitarian, but yet they're very architectural. They go all the way from iconic stadia, such as here at Notre Dame, to iconic Tiger Stadium. They're also really interesting piece. Tiger Stadium's kind of crazy. They have dormitories built into the bottom of the stadium. This was all Louisiana politics. Every structure is a little bit different. There's a story behind every one of these stadia. They date back. The ones I'm going to talk about aren't our professional franchise stadia where they're redoing them every 10 years to get the luxury suites in. These are the historic structures. Many of them date back to just after the turn of the century when college football was at its peak, and back to the WPA. This is an example of a municipal stadium. It looks very low-key. This was built by the WPA. And actually has a lot of history in of itself. The Boston Braves played some of their earliest games here. But the other thing about stadia is that they don't hide anything. There's not what you see is how they work. Their bones, their structure is exposed. They're wide open to the weather usually, very exposed to the elements. But what you have is there. The structure is visible, and the repairs you do are going to be visible. And it's all right there out in the open for you to see. And the thing that really is neat about stadia is that the people that use them have this intrinsic, visceral feel. They love their stadium. They have a connection to it. It might be where they played football, where their father played football, where Newt Rockney's team was. It's all very visceral connections to these buildings. And you can't underappreciate that. So they're really neat structures to work with. But because of all these, there's all these things swirling around with them. So when we work on a stadia, we have to respect all these different interactions. They're very visible. What you do to them is going to be apparent. They have this deep connection to their users. But we're talking about a lot of public safety here. There's a lot of people. When they are used, they may only get used 8 times a year, but on that day there might be 80,000 people there. So we have to use sound engineering principles to maintain that public safety. Economics factor in a lot. For some places, they're money makers. For most places, municipalities, they're money losers. There's not a big, strong revenue stream for a lot of stadia, so they can't rebuild every 10 years. And the other thing is, I think sometimes as engineers, we start thinking that we're the be-all, end-all. But when it comes to stadium operations, the operations is far more important than the structure itself. There's more on the line with the hot dog vendor really in terms of their return and how the stadium's used, how it generates revenue, than the structure really has to do. So we have to respect that the stadium, though we live in the structure world, there's a lot more that goes on there than just the structure. So they have some very particular challenges when it comes to rehabilitation of these type of historic stadia. A big one is structural. There's a lot of seismic concerns. If you look back, this was a WPA era building. There's maybe ties every 18, 24 inches for 4 feet above and below the connections. They're really poorly detailed by today's standards. So we have to be very aware that if you start digging too deeply, you're starting to look at some major upgrades and getting some of these structures. You look at the aspect ratio on these columns, it might be 30 feet unsupported, unbraced length. It's really hard to make these structures work if you have to upgrade them. So the seismic concerns are big. Building code issues, other aspects are very important. This is out at a stadium where the stadium was expanded at one point in time. So you can see the upper section of the stadium was built to modern standards. And you can see that the area, the seating bowl area, is served by the VOMs, the entrance and exits. Of the new area, the area is about half. The area for each VOM is about half the size, yet the VOM's twice as big. That means if I want to bring my lower bowl here up to code, I'm going to have to quadruple the area of entry and exits. That's a really hard thing to do. You lose a lot of real estate. At this stadium, they would have lost something like 6,000 seats if they had to update their egress to meet current code. And they have 20,000 people on the waiting list here for season tickets. They can't afford to lose 8,000 seats. So we have to be very cognizant. That's a very important driver for the owner of this stadium to not trigger those upgrades. They also have very unusual load paths. We don't do as much nowadays with folded plates and continuous diaphragm action that they did then. But they have very robust, although the system looks very light and airy, these folded plates are very robust. That's going to come in as a factor later on. They use a lot of truss bars. There's not a lot of shear reinforcement in a lot of these structures, so you have to really think about how they work. And you get some unusual damage types, things that we're all used to seeing, the bridge deterioration like Dave just talked about. But in stadia, as we're going to see, we have very different deterioration types. This is one municipal stadium that was pretty heavily deteriorated. The kinds of damage that we see at these historic stadia, one of the biggest ones is corrosion. It typically looks like this. We get deterioration of those bars in the back of the seating risers. We get joint failures. You saw that earlier in Dave's presentation. Same things happens here at the stadia joints. That's the classic location of the heaviest damage. In extreme cases, we get organic growth. You see this more often in municipal stadia as the deterioration progresses. It's usually a sign that you're in pretty deep trouble when you have to go tell them to mow the stadium. And by far the biggest one, the most pervasive damage is freezing and thawing damage. This is a core hole taken through one of those folded plates, showing the deterioration that happens. Of the two, of all these four, corrosion and freezing and thawing are really the keys. They're what govern most of if you're in repairing a stadia, it's usually related to those. The corrosion's a little bit different when it happens. It's usually not chloride-based, although we have seen some of those. It's most often carbonation-based. These were built with fairly low cover. A lot of times there's a lot of honeycombing. These complicated structures usually were built by the concrete was placed by hand and pounded into place. So there's a lot of honeycombing, a lot of carbonation, and low cover. So the approach to repairing that corrosion is a little bit different than a chloride. The most insidious one, though, is the freezing and thawing that happens. Right? Obviously, that happens when water gets into the concrete, freezes and thaws, that ice expands and contracts, causes it to break. Right, nowadays, it's not as big a problem because we use air entrainers now. But those really came into their full being in the 50s, 60s, and 70s. But that was after most of these stadia were built. Back in the WPA, they weren't using air entrainers at all. And it's a progressive failure. It really starts at the surface and digs its way in, and it can become very, very widespread in these structures. So when we look at, here's classic carbonation corrosion, happened in a stadium. You usually see it just like this. It's the backs of the concrete will fall off. exposing the bars. And in this case, it was exacerbated. You can see it's all damp. This is a low airflow was in this structure, and it had huge condensation problems. You had a damp, moist underside. Concrete's very cold, and you had a lot of condensation. Freeze-thaw. This is an extreme case of freeze-thaw damage, but you see there's just this pervasive cracking that happens throughout the concrete. It's almost like concrete baklava almost. It's all these little layers of pieces. But the thing that we have to remember as engineers, it's a little bit different than the delaminations that we see with corrosion. Right? With corrosion, you usually get one big sheet, one big delamination happens. This is really a series of a lot of very small cracks. They don't necessarily interconnect. There's a lot of, you imagine it's all little plates of little cracks that aren't necessarily interconnected. It means the damage is maybe not as bad as it looks. A lot of people might just see this core and condemn the concrete. Say there's no way we can save this. Look at the extent of the damage. In this case, it actually is pretty bad. But like that earlier one I showed you, there's actually a lot more structure left than what you would think at first glance. Right? Fixing the freeze-thaw is usually what controls the repair of these structures in northern climates. Right? It covers an enormous area. Almost every bit of the concrete is affected to some degree or another. Sometimes the damage is limited to the very surface. Other times it extends very deep down into the concrete. But remember, that cracking is not necessarily interconnected. But what it is there's so many cracks, it makes the concrete very fragile in the direction parallel to the cracks. I'll show you an example of what happens. But it's very fragile in one direction and still fairly robust in the other. Makes repairs a little bit tricky. And what we really need to do to keep this from getting worse is really minimize the moisture exposure in the future. Right, so what do we do when we approach a stadia? We have a historic structure such as this. What are the different parties thinking about? What's driving people to do their different work? There's all these different motivations. Everybody at the table has some different things. We think about building code, expected life, this whole set, and we'll walk through them all. There's all sorts of things happening. And if we think about the different parties, I'm going to start with the contractor who's going to do the work. The contractor's worried about the building code. Right? We have to make sure that it's safe. He's concerned. And just as a warning, I'm doing this very broad brush. These all apply to everybody. But I'm thinking here, what are the really drivers, the most important things? So forgive me for not getting into the nuance of each one of these. We're trying to paint some broad brush here. They're really worried. The contractor is very worried about cost, right? He's trying to get the job, and that job is awarded based on price. So he needs to make sure the contractor needs to get a valid bid that encompasses the scope of work, but yet is competitive. They want reliable repairs. We don't want to have callbacks. Wants to be very predictable. Contractors like predictability. Doing things on the fly is not conducive to keeping that cost low. They're worried about the appearance because that's going to be a big driver to the owner. The maintenance requirements. The contractors actually take a lot of pride in what they do. They want to be able to show that project off. And they want to be efficient when they do the work because that helps, again, gets into the cost. When we think about it from the engineer's perspective, the engineer is very, very concerned with what the code requirements are, the expected life, because the engineer's promised something to the owner. That's what they've designed for. The engineer is really worried about the quantities, the damage amount, because if the engineer gets the quantities wrong, then the bids come in wrong, and everybody gets upset now that the bids coming in well outside of the estimates. So they need to know how much work there is to do. They want reliable repairs. They also want the predictability, and there's a certain amount of pride and reputation. And again, I'm painting very broad brush here. And if we think about the owner, there's a lot of other things the owner is concerned about. They want the building code, expected life. They don't want to be back. Cost is important. They've established a budget, and they want to get through it. They want a very reliable repair that's predictable. A lot of times, speed becomes very important to owner of these stadia. There's many events scheduled. There's only a certain amount of downtime we have. We have to get in between commencement and maybe the spring football game and the fall football game, and there's a concert for senior week. So there's a lot of speed that gets into it. They want to know what kind of maintenance they have to do, And there's also, these are owners. People don't sell stadia. It's not like repairing garages. You're not going to repair it and turn it around in 5 years and sell it off. You know, if you're working on a stadia, you're going to have it for the next 30 years. So what do we do with this kind of situation? Right? The damage is very complicated. There's all sorts of things going on. There's all different types of damage going on at the same time. It's widespread. A lot of times I can't see how much freeze-thaw damage there is ahead of time. It's not visible. It's inside the concrete. So a lot of conventional concrete repair techniques fall short. Right? And then there's the idea, like Dave was talking about earlier, you know, what are we trying to get a new structure, or are we trying to stabilize what's there, get some more life out of it? What's the best long-term cost solution that meets all the objectives, right? Good as new, a brand new structure may not meet those objectives, right? You may have to require, if you want a like new day one just built for these structures, you're going to have to rebuild it. And that's not necessarily what you want. So we think about this on a repair continuum. We have a kind of a cost associated with where we end up, right? On one extreme, we want a like new structure. I want to get rid of every bit of damage that's out there. I want to get rid of every crack, every little bit of freeze-thaw damage. This is what you're going to get. You take it out. You can see here, this is that fragility I told you. It's very fragile when you get freeze-thaw damage. And kind of one of the key tells here is this pneumatic chipping guns down on the bottom. This material, with freeze-thaw damage, you get on it with a rivet buster, you could take the entire, you could put one guy with a rivet buster and give him enough time, he'll take the stadium down. That's not what we want. You're very fragile, you could peel it apart, but it may not be the best. The other extreme, you could do what this municipality did and do nothing and be back at this case 20 years later, where there's extensive damage. There's actually a piece of plywood there covering a hole. There's moss growing here. They were using this for high school football game. This was being used every other weekend for high school football games. A little frightening. Anybody want to sit in this seat on top of with your feet on the 3/4 inch rotten plywood with a hole underneath it? So that's the other extreme. You do nothing. What we really want to shoot for then is the sweet spot. We want to find that sweet spot where we're doing what's needed, we keep it safe, we repair what's damaged, what needs to get fixed, and we leave what's left and stabilize the structure. We want to live with what it is, get it to where we can fix it and work with it, and hold it there. Right? We don't want to be brand new, but we want it to be safe and workable. So that's a tricky spot to hit. So what we have to do that is we have to share these common goals, really, of performing the minimum repairs necessary, but still doing enough that we get reliable repair. And we want to be safe, make sure it's done correctly. We want to get some level of predictability and scheduling. So key to that is really getting all the parties involved in communicating those motivations and expectations early. We need everybody to understand that it's not going to be like new. It's not going to be a like new. It's going to be a stabilized structure that's still safe. It may not be the prettiest thing ever, but we may not need that. And we want to be flexible. This whole approach is a little different. You're going to have to teach some old dogs are going to learn new tricks when you're doing this. And we're going to have to do some work on the fly. Typically requires a lot of on-site inspection. So to do this, we really have to educate. There's a lot of upfront work to educate all the stakeholders, the building code officials, the owners, the contractors, the engineer. We want to make sure we do enough, but not too much. We have to use a lot of on-site inspection to make sure that enough is getting done. We want to do enough work to get some predictability in the bidding, and we need to be pretty agile. We need to be nimble, be able to think on our feet. You're going to find unexpected things when you do these structures. So how do we do it? I'll take a little bit of time now and just walk through quickly, but really that's the focus is these different things to think about. How do we put it into play? So now here we go, putting the plan into action. The first thing is to get a good handle on the extents. It's a stadium to first find out that quantity of damage. I told you a lot of it's hidden. This is an impulse response map. We did non-destructive testing, basically at every seat in the stadium. We've got 80,000 something hits here to figure out which sections are damaged, how much, and to use that to generate estimates of cost. You can take, once you get that estimate of where the damage is, how much it's going to cost to fix it, You can define that scope of work. You get all the partners together. You get the building official with the owner, the engineer all together and say, this is our approach. Does everybody buy in? Do we understand it? All right, it's not going to be brand new, but it's going to be safe, it's going to be workable, and it's going to do what needs to get done. Sometimes there's a big question about how to make it safe. If you get one of those cores that, remember the concrete baklava core, right? People were sitting around saying there's no way that structure's safe. So we had to prove that it was. We did full-scale load testing. In situ, full-scale load testing with loaded water barrels on the as damaged concrete. Remember, it looks bad, but they're not necessarily interconnected. This passed with flying color. It wasn't even a hint of. It didn't even come close to the limits on what it could be. Right, that folded plate does a lot of good. It does a lot of help for you here. So we did, if necessary, you do load testing or ensure that it's still going to be safe. Right, you're only working this building's being used 8 days a year, but on those 8 days there are 60,000 people in it. You better hope that that event doesn't happen on one of those days. Right, a key to the approach then that we've used on these stadia is then using to avoid doing that chipping. Avoid the chipping guns by using hydro demolition. The hydro demolition, the beauty of it is it's self-selective. Once you get it dialed in correctly, the hydro demolition takes out the most damaged concrete and leaves what's sound, without that progressive failure that you can get when you're doing it with chipping guns. If I take a chipping gun, I can peel the structure apart. With hydro demolition or working straight down from the top, it's fairly robust. So we use the demolition method to actually do the discriminatory work. Where it's bad, the hydro takes it out, and where it's good, the hydro leaves it. Although regardless, you still are going to end up with some areas that are heavily damaged. And there's no way around it. There are some full depth repairs. They're still here. This is showing it in process. Some of the concrete's going to have to come out. Some of that really rotten things are going to come out. You can't just say you're going to save it all and leave it. And that takes a lot of inspection to accomplish that. This is in that stage, the awkward kind of teenage stage there between hydro demolition and all the prep. So there's a lot of paint. All that orange is from inspectors walking around on it. We used a lot of cans of paint on these different stadia. But you're there working hand in hand with the contractor so they know what you're looking for and how to get it. Come in, do the concrete repairs. We're doing solid, sound concrete repairs according to good practice. Tie it in, make sure that load transfer is still there. But it's all individual. We're not doing that. See the fundamental difference between this and that wholesale demolition that you saw earlier. Much more controlled, much more precise. Do a lot of quantity and inspection tracking. This is all going to be done on unit cost prices. Generally, you can't ask a contractor to do this on a lump sum price. They have no idea what they're going to be getting into. So it's a lot of quantity tracking, a lot of inspection, a lot of color codes telling us what type of repair, what quantity it was, what stage it is in the inspection and approval process. Also have to add to this a lot of quality control testing. Extensive pull tests to make sure the repairs are doing what you want and that everything's working the way it should. And we come in and prepare for the waterproofing. I said a little bit earlier, we have to be ready that it's not going to look just like new. And this is one of the key components of that. This is all doing touch-up where it's really needed. You can see the epoxy paste being applied to the faces of the risers. But not everywhere. It's not going to look like new. We could do like new, but it's going to cost more and not be a good ROI. So we come back in, do some mock-ups early on, and make sure that, this surface isn't going to look like, it's going to look like this, Mr. Owner. Are you okay with that? And the answer is usually yes. But everybody is on board at the same time before the project goes into full swing. Everybody's on the same page. Once all that's done, you come in and you do the wide-scale application of coating. Coating is pretty key to these because you have to stop that long-term deterioration. You have to keep that water out. And like Dave was talking about earlier, this now becomes a maintenance issue. This isn't going to be a do it and walk away because you've stabilized the structure. You need to keep it stable here. There's going to be a lot of touch-up work. If you're going down that path of stabilize, be ready to be repairing this coating, do touch-ups and top coating. Some places we're doing it on a 5-year cycle. It's a lot of coating, but it's cheaper and better off in the long run than rebuilding the whole stadium. And the joints just the same way along with the joints. There's a lot of upkeep. It's in the long-term economic plan that if you're going to go this method of stabilizing, you got to be ready to spend the money in 5 years, 10 years to redo those joints and make sure it is stabilized. Go through do a lot of quality control testing of the concrete, of the coating, make sure all that's up to snuff. Make sure if there's anything that's not, you fix it now while everybody's still on site. So then to wrap it up, stadia work is really interesting. I like the structures. They're a lot of fun. You see the bones of it. It's all exposed. There's this visceral connection. People really know and love that. They can tell you all the stories about the stadium. But they do present some challenges to conventional thinking. We're not going to repair this the same way we'd probably repair a parking garage. To pull it off, you really have to align everybody. You have to align the goals and the understandings and the expectations of all the parties. You need the building official, the owner, engineer, contractor, all need to be aligned. You really need to be careful, prepare the concrete right, not go crazy, because you can tear these things apart if you're not careful. And you have to do a lot of cooperation and inspection between the day-to-day, that superintendent and the engineer doing the inspection really have to be on the same page. We get up on these jobs, we start the day together, talk about what we're going to do, work throughout the day. At the end of the day, you sit down and you say, what did we get done? Is stuff going right? Is it going wrong? You really have to work together. This is not a place for an adversarial relationship. It's really a place to cooperate and work together to get everybody to the right end. So with that, we're actually staying crazily on topic, but we'll get some time to answer some questions.
When you did your load test, did you load test the risers and the treads separately? Like with the tubs, I assume those are just for the risers?
For the load testing, do we do the risers and the raker beams is what you mean? Or the risers and the tread? They're a folded plate. They're all together. It works.
You mentioned it in the context of freestyle damage?
In freestyle. We were looking at vertical. That structure we actually did vertical gravity load test, which is what you saw. We actually did lateral load tests on the structure as well to look at the effect of any deterioration of the plate on the lateral load resisting system. So we pushed sections against each other, reacted them, and looked at the motion and looked at the vertical load carrying capacity. So there was nothing specific to the riser portion itself. It was only as it caught in its folded plate action and in the lateral load test how it worked on diaphragm action.
So very interesting comments I thought about freestall. Is there sort of a rule of thumb that you use as to the depth of that member and how deep the freestall damage is, and leads you to conclude that that's beyond repair?
Right. We have found it really becomes apparent during the repair itself. At some point, you physically can't prepare. Once the damage reaches a certain amount, certain depth, you're limited actually in your prep. Once you start doing the prep, you punch through, and there's no way to avoid it. You need, what we found is once you get less than 2 inches of uncracked concrete, I'm not going to say unsound, but of concrete with none of those freeze-thaw cracks. Once you get below about 2 inches, it becomes very difficult to do the demolition without that. And actually, at that point, your repair gets so thick, your remaining concrete is essentially a stay-in-place form. It's tough to come up with just a number as to. It's discovered during the demolition as to when it becomes a blow-through, and really the blow-throughs happen because the workers on the guns physically can't do any more work without punching through. And if you wanted a rule of thumb about that, is really once you get too much past the reinforcement, if the freeze-thaw damage is much beyond the reinforcement, you're not going to be able to pull that off effectively, leaving it in place. It just becomes a practical issue rather than a structural.
Are you, in most cases, replacing or sealing the joints like with a caulk joint, or are you putting in some type of a joint and member that will accommodate more movement? I've seen a lot of failed caulk joints in those kind of structures.
Right. There are a lot of it comes down to cost. We'll go in usually with a multiple layer system. There'll be a true At the true expansion joints, there will be some sort of a movement accommodating primary seal joint, but that'll usually be buried with an aesthetic or a architectural sealant joint on the top of that, with the sealant joint shedding the majority of the water, and then the primary joint seal being below that and protected from ultraviolet, from contact and everything. So we'll use a multiple layer system because joints are the key, like you found on your bridge.
All right, thank you, Matt.
Thanks.